Okay, so now that we've taken a pretty detailed look at equilibria applied to acid-base systems, let's now take a look at equilibria applied to solutions involving the ability of different solutes to dissolve in aqueous solution. And this is going to be known as solubility equilibria. So the thing that we're going to have to recall here from our Gen Chem 1 material would be solutions and solubilities. Okay, so you may remember there was a solubility table that we use to qualitatively predict whether a particular solute, specifically ionic compounds, can dissolve or are able to dissolve in water. And they range from very soluble to insoluble. Well, the truth is, things that are insoluble, so insoluble compounds, actually are soluble, but to a very small extent. Okay, and what we're going to do in this section is take a look at these compounds, not just the insoluble ones, but the soluble ones as well. And we're going to apply some equilibrium principles to the solubilities of ionic compounds. So let's take a look at an example of having a saturated solution of silver chloride like this. So we have here saturated. Remember, saturated means that we can't dissolve any more of the solid in there. So saturated solution of AgCl. Okay, so we have our silver chloride, solid, dissolve it in water, and we end up with our Ag plus and our Cl minus. So if you look at your solubility table, you would actually see that AgCl is not very soluble. In fact, we consider it insoluble in H2O. But the truth is, even a little bit of it does dissolve. And even the little bit that does dissolve dissociates completely into the Ag plus, the silver ion, and the chloride ion. And we can actually write an equilibrium expression for this. So the AgCl, right, reversibly to form Ag plus and Cl minus. And then if you write our K expression, right, we end up with, just like we've done before, Ag plus times Cl minus divided by the AgCl solid. As we know, right, this here being a solid, the concentration is not going to change. So that's a constant concentration. We can move this over to the other side. So we end up with AgCl times K is equal to Ag plus times Cl minus. We have now a constant times another constant. We're going to call this a brand new constant, now with the subscript Sp, and the Sp here stands for solubility. Product. And that's equal to the product of the concentration of the Ag plus and the Cl minus. This is just another example of the equilibrium expression now applied to solubility. We have now the K subscript Sp. Well, we're going to be using the same principles and apply them now to this situation. So if you look up the Ksp value for silver chloride, what you will see is that the value is very small. It's 10 to the negative 6. Right? And because it's 10 to, this is a very small value. And as we know, when we have K values that are really small, it tells us that the equilibrium lies to the left. right? So that means if you were to dissolve some AgCl in solution in some water, we're actually going to have a much higher amount of this being in the undissociated form, very small amounts of the ions, because it doesn't dissolve to any great extent, right? And that's the general principle that you want to think about when it comes to the solubility of different solutions, right? This here is called the solubility product expression, which doesn't look very different than all the other equilibrium expressions we've written in the past, right? The reason why we don't have anything in the denominator is because what would have been in the denominator is a constant, which is the concentration of a solid. So we just moved it to the other side. Okay, so generally we can say the magnitude of KSP, okay, is going to tell us the solubility of an ionic compound, determines the solubility. So smaller KSP value, what that means, less soluble. Okay, larger KSP value would mean more soluble, right? That's a general trend. What we need to make sure though is that we want to compare similar salts though. Meaning if you're going to compare KSP values, the salts that you choose to compare need to be similar, meaning they must produce the same stoichiometric amount of ions. We'll take a look at some of these here in a second.